Kia ora koutou and welcome everyone to this morning's GNS Science Seminar. I'm pleased to have Simon Cox with us presenting his work around groundwater models this morning. Just so you know, coming up next in our series after Easter, we have Vanessa Tanner from Heritage New Zealand, who's going to be talking to us about what we need to do before we dig and working under archaeological authorities. So please join us for that. As a reminder, if you could please keep your videos off since we have a fair number of people joining in this morning, and we'll save questions to the end. So please use the raise hand function at the end if you do have any questions. So thanks for that. And so I'll just quickly introduce Simon. Simon is a principal scientist at GNS Science in Dunedin. His early career was dominated by interest in tectonics, the Southern Alps, Antarctica, and mineral exploration. However, during the past decade, he has focused on geological hazards, characterizing landslides, the Alpine Fault, earthquake hydrogeology, and shallow groundwater systems. Simon maintains close tie with local iwi and Maori, supervises research students, collaborates internationally, and has a wide network of science and end users. So welcome, Simon.
Thank you, Katie. Tēnā koutou katoa, everybody. It's quite a strange thing to be talking to lots of people online, but people are very important in these problems. And I started this talk yesterday and I had a picture of South Dunedin and on my title slide, and I decided to change that to this picture here with the South Dunedin community hui. We have regular ones in Dunedin because this work really is about people, and I just wanted to make sure that I keep that at the forefront of what I'm talking about today. And as a result, I also want to acknowledge that although there's, we're talking about sort of scientific problems and things, there are people who are experiencing the issues associated with this sort of problem right now. So thoughts go out to people on the eastern North Island, but also Eastern Australia at the moment, and the cleanup from various flooding. So take a moment to think about them. I guess this project is something that I've been kind of pulling together out of a whole lot of different strands of work, and I've shown them here. There's work I'm doing under the GNS Groundwater Strategic Science Investment Fund under Project 4. Rahir Westerhoff runs that, and the project's led by Connie Schritter, and I'm working on kind of in the space of urban groundwater there. But I'm also working on a Marsden project with people from the University of Otago and Boudica Scientific, which is called the STRAND Marsden Project, looking at the effect of flooding hazards on property market and financial systems. But I've also been working for the New Zealand Sea Rise program, so bringing together all these different programs in order to do this work. I guess I deliberately threw in empirical geometric models of groundwater inundation as a consequence of sea level rise, and it's a really quite a scientific kind of a ugly title that'll frighten people off. And I just wanted to sort of start by simplifying that and just remind people that, in my view anyway, empirical approach to science is when you're using observation or experience in order to solve a problem, rather than necessarily just pure theory and logic. So it's there's different approaches in science, and empirical is a very well-known approach. I guess I know it very well anyway from mineral exploration, and the classic example of empiricism near Dunedin is the Macraes mine, where essentially they have drilled now nearly 1 million meters of drilling and analysing for gold. Basically 8,290 holes or so, probably more now. But that whole approach is chasing the gold. It's kind of understanding it from taking observations and then stepping out from what you know and building on that experience in order to make some informed decisions. And in fact, in many cases, Macraes are not concerned at all about where the gold came from or how it got there, despite as we might want to to come up with some sort of theoretical background for it. Actually, they do most of their exploration through just understanding what they've got and stepping on from it. And it's a method that works extremely well in exploration. So today I want to take you on a bit of a roller coaster. It's a 4-part kind of roller coaster. I want to start by taking you up the hill and across through a background or on groundwater, and this get across the notion that hazards not necessarily proportional to elevation. Then we'll talk a bit about different types of models that you could apply, and then I'm going to give you an example from Dunedin of how you can apply a geometric model, which is essentially just using the geometry of what we know is presently here and how it behaves in the groundwater, and then talk about compound hazards and the effect and the problems that we have here in Dunedin. So that's the sort of outline of where we're going. And I guess to get there, we really just need to perhaps also just define this concept of shallow unconfined groundwater and how that's slightly different from a lot of the groundwater that most people might know about. Shallow unconfined groundwater is basically where the upper surface of the water table here is essentially in equilibrium with the atmosphere, so it can rise and fall. It's quite different from down in deep aquifers where you can have it confined underneath an aquitard. And so it's really, we're dealing with this sort of area around beside the coast that will be influenced by the fact that sea level is going to rise and impinge itself upon the coastal margin. And as it does that, it has an effect also on the drainage of systems down into in towards the sea. And we're really asking the question of when and where will land become unusable due to this hydraulic link in these low-lying coastal areas, or even perhaps between the groundwater surface and the groundwater and surface flooding. The motivation for it, well, you can pull any statistics you like, but basically 65% of New Zealand's population is living within 5 kilometres of the sea. I mean, we're a coastal country. There's no question about that. And a lot of our wealth is associated with real estate, and our savings are in real estate. So it's really important to us that we, in our houses, that we don't have the situation you see down below. And in terms of our finances, we've got 60% of the value of our 4 largest banks' loan portfolios are in housing. So if you just look at the housing question itself, it's really important. But along with housing, there's all the social issues as well. And we're going to have an increasing amount of sort of sea level rise and groundwater storm surges and precipitation. From a science perspective, these are coupled and combined problems. They're really tricky problems because of the way that the hazards sort of behave together. And we need much better ways to assess the hazard and risk. And I guess the key thing for this talk is that it's just not feasible to develop fully numerical groundwater models everywhere, and we don't have the data to calibrate them. So we need some way of improving what we're doing for local communities. And my personal motivation is around sort of serving South Dunedin, Otago Regional Council and my city, and serving that community and trying to come up with ways that individuals like this person down here can think about how much risk they want to be exposed to. So if we go to Dunedin, it sort of stands out there as a big hazard area in this report that came out in November 2015 from the Ministry for the Environment. And they produced this report and highlighted the number of houses that are sitting down within, close to the high tide mark and sea level. And they had a series of maps that had these sort of caveats written along the side. The elevation bands shown in this map are not hazard zones. And it was very clear in that, but the immediate thing that came out of that was this kind of response in Dunedin was, oh my goodness, what's going on? And, and it was then we started to see all sorts of sort of messaging happening around the hazards that we face, because we just had a major flooding event in 2015 across part of South Dunedin. If we look at the low-lying area of South Dunedin, it is very low-lying. You can see the land elevation map here, and I've coloured pretty much anything that's less than a metre in New Zealand vertical datum 2016 is blue. An important thing to realise is that there are variations also in the ocean and harbour levels and the ranges of the harbour and the ocean. So people think of sea level as being zero, but it depends on what datum you're in. And in New Zealand vertical datum, the harbour level for 2019, the mean level was minus 0.2. And the sea is actually minus 0.72 metres during that period. And the median level over a long time is slightly negative. So it does vary. And then you've got a tidal range, 2.7 metres here on the coast, and it gets amplified up the harbour because it's sort of essentially squirting up, and the topography generates this greater tidal range in the harbour. So what happened kind of immediately and in the process of looking at that kind of country risk and New Zealand-wide risk was that people built bathtub models with LiDAR, and essentially they just painted anything blue with different levels of sea level that they wanted to put onto a LiDAR model. It was very easily done, and so here's Dunedin painted blue, and I've deliberately put all the houses there just to remind you that it's actually people and buildings and the community that you're actually tarring with this blue brush. Key point for Dunedin is that we have this zone of reclamation, this reclaimed land along here, which sits about 2 to 3 metres above the vertical datum, and we have a whole series of dunes which sit between 6 and 20 metres above the sea. So at the moment we're very much protected, and if this is going to flood, it has to seep through in groundwater, or for some sort of storm surge to come over the top of this land or breach through the dunes. And at this stage we've never had any breach from the sea or over the dunes and in that direction. In fact, the real problem we had with flooding in 2015 and previous events in 1968 was runoff coming off down the hills, plus the fact that there's no gravity able to take drainage from here, and it ponded up against the hills in this area. And the people in South Dunedin know that. And I think I deliberately put that photograph of the hui back there because people are concerned, but they were being told at that point that sea level rise was going to cause all sorts of problems, when in fact the problem that we have at the moment is around infrastructure and the lack of ability for it to naturally flow out. So we have to pump the water out through the system over here and into the harbour. So what that model was saying is what I call a bathtub model, which is where you have a level of groundwater that you're assuming is in equilibrium with the sea, and that when sea level rises, the groundwater will rise by the same amount. And we see those applied all around the world. There's lots and lots of them at all sorts of scales and all sorts of studies which tell us what exposure we may have to sea level rise. But it's not necessarily correct. If you look in this Dunedin model, you see this little purple spot. And in fact, that purple spot is the Logan Point Quarry right beside the Dunedin Stadium. It's 400 metres from the harbour, and it's 39 metres below sea level at the moment. And it's cutting down into a basalt rock because that's what they're using for aggregate. And there's a little bit of water in there, but the sea does not seep in there. We don't have a 39 metre deep swimming pool. And it highlights the fact that geology is important, that in the subsurface, it's critical to understand what's going on. Another thing that shows you this sort of silliness of a bathtub model is that it doesn't account for distance inland. And if you take the Netherlands, 2/3 of the Netherlands lies below sea level. So although hazard may be a function of elevation, it's not equal to elevation. And that's why in that earlier report, it was said not to be used for a hazard assessment. But what inevitably happens is people take these regional scale kind of approaches, take a elevation as a proxy, and they apply it locally, and immediately you get the community upset because they're saying, well, my house is never flooded and it's sitting, very low. So you have to be very careful about how you apply these models. And the problem is that we're not putting in what's really happening in the natural system. So this is a cartoon to try and change the bathtub model that I showed you before and include some concepts around the different types of sediment that you might have, different aquifers, some things in the subsurface, but also the variations that you get on the top. And so what we're really expecting to happen is that the water table here, marked with a blue line, may well go up and equilibrate to a certain extent locally at the beach. But there's already in the water table, there's a slope associated with it. It's not flat. And there's the slope and the bumps depending on where it's being recharged and where it's draining away and whether it's in permeable or impermeable sediment. And we may well get ponding and groundwater emergence quite some distance away from the coast, where if you took a horizontal model, you would have quite a different result. It also starts to impound on rivers and estuaries and the water that falls from rain and from the rivers. And to highlight that, I'll just show you now the sources of water. And if you think about them, that you could have rising groundwater here causing flooding. You could have marine inundation in the sea bringing water in, but you also get these other surface ponding from the rain and rivers and estuaries also causing flooding effects. And the tricky thing about these guys are that you get a compound effect and non-linearity because they actually are dependent themselves on the position of the water table, which is where it starts to get very difficult to model those flood effects, especially into the future if this is a sloped water table. Now add to that the complexity of an urban system, because we're really concerned with the urban areas and where we've got something in the way, some sort of consequence of the sea level rise. And in the urban system, certainly we have drainage, which will keep the water table down, especially if it's leaky old pipes like in Dunedin that act as drains. And we've got other areas that will eventually become inundated. The drainage will become inundated and unable to flow out because of the sea level rise. So we've got this sort of sloped modulated system, and depending on what area you're in, you've got this sort of balance between an urban system and a natural system, somewhere in between, and all the problems associated with it. So it's not easy. And our job as scientists is to try and provide some sort of picture of the enemy and how to deal with it. And of course, you get all sorts of different responses. And I don't know if anyone here is old enough to remember Dad's Army, but you get different sorts of responses to it. And I think the key thing from my perspective is a kind of we need to take a Wilson's type approach. Come to me with solutions, not with problems, and trying to think through what is this thing that we're dealing with, and getting more information in order to solve the problem. So one way to do it is to build dynamic groundwater models, and this is the kind of Rolls Royce, I suppose. A dynamic model is really something where you're looking at the changes and simulating systems as they change over time. So Lee Chambers has been working on a model for Dunedin. There's a picture of it here, where it's a flow model that's based on the principle of the groundwater change is related to recharge minus the discharge, and then you set a whole series of parameters on permeability of the ground, the storage, the flux, and the velocity, and so forth come out of there. And this is sort of a standard modelling process for groundwater. It's very good for examining what are the key factors that create the equilibrium that we see, and then for tweaking those and seeing what would be the impact of disturbances. So for changing sea level and then seeing what would the effect of that, it's a really useful kind of approach. But the part of the problem is that this numerical approach is it simplifies variables down to sort of 40 by 40 meter cells. In this case, that's quite a detailed model. But they're mathematically complex and they're computationally quite expensive. So while you can develop a model for a place like South Dunedin, you can't do it over all of New Zealand. And in fact, we don't have data to apply for a lot of these areas. So that approach is great, and I would be the first to advocate we should be doing more of it. But we also need some other way of dealing with the wider area of New Zealand. And another way is to take these empirical models. And essentially an empirical model is really this sort of a more simplified way of using observations to represent the system at the current point in time. And essentially we're collapsing the parameters down into a single observational proxy, such as groundwater level, and then looking at the changes in that and trying to eke out what's driving them. It's much more difficult to characterize the effects of system disturbance and what it might look like in the future. That's where the downside of it is, but it's much, on the other hand, you've got something that's mathematically and computationally straightforward, and you can generate high spatial and temporal precision. And also you can transfer it into a probabilistic sort of framework fairly easily for hazard and risk assessment or for engineering. So just to give you an example, here's Christchurch. After the earthquake, a lot of work was done and EQC invested to install a whole lot of piezometers, pipes in the ground that were measured every month, and that data was used to build up a picture of where groundwater is in the at different levels across the city. And we built these maps here. Sorry, I'm just moving a thing there. We built these maps in a report with Tonkin and Taylor that ended up with a very spatially precise set of essentially maps of the groundwater. The water table is a median or a 85th percentile or a statistical surface representing where you would see groundwater and the depth to water. They're spatially precise, but there's always questions around the temporal uncertainty because they're taken off a series of observations after the earthquake. But it's an empirical approach, and in fact, to have 950 sites across a city like Christchurch at the time, we thought was pretty amazing. You don't normally see density of data like that. I've frozen, sorry. Let's see, what have I done? Okay. So in 2017, they changed from doing manual dips of all of these sites, and they set up a new network which was automatically logged. And that's shown here in red dots. And we changed from having essentially sort of 12 to 58 observations per year to having a really precise, temporally precise set of observations. And this is an example of one of the sites in the hydrograph, that the data that we had of individual observations, and how once we started to observe at 10-minute intervals, that we had been missing a lot of data and information. So here, this had been going up and down and up to the surface level. In fact, the water had been getting right to essentially to the top of the piezometer quite regularly, but that wasn't represented in the data set prior. Now, there could be a number of reasons for that, but probably the most likely is that the observations of dips weren't being taken when it rains, and that people weren't going out and actually doing field work in the rain. They were waiting for the fine days. So that was a major change in the collection of groundwater, but it was a real insight for us to then start seeing how do you do these shallow groundwater networks. So they're just measuring in the top 6 meters or so. And a number of places have got networks in, but the kind of next largest that I know of anyway in New Zealand is Tauranga, which has 97 sites across the city and out through Papamoa Spit, recording at 15 minutes. And these are all useful for looking at, what are the forcings and what's the effect of sea level rise going to be? What is the complexity of the groundwater system, the shallow groundwater system? And Dunedin, of course, has its network with about 26 or 27 sites. These are all at the same scale. So sorry, I meant to say these are all the same scale density. So you can see the density of the dots in each of the centres. So here's Dunedin's one, similar density, but it's a much smaller area, and it's a very focused kind of set of water forcings that are coming into the groundwater system. So let's look at Dunedin a bit more closely. Here's our monitoring network, and the water table here is shown as a map with colour representing elevation, and so it slopes down towards the sea and towards the harbour. And the way to think of it is a bit like a bubble on your table. It's sitting above sea level. Within the ground, you've got this sort of low-lying kind of ridge of water where it sits up, and it's sloping off down off the hill and off the hills on the peninsula as well. If you subtract that from the LiDAR elevation, you can get a depth to groundwater model. So here we have in colour showing you the whereabouts it's a long way to groundwater here in the browns and the orange colour, 10 meters or so. Greens and blues are less than a meter. And in fact, we've got a problem in this area. The modelling is difficult, and we've just installed some new piezometers in here to try and improve the model a bit because of the topography that's there. But we get these depth to groundwater models. So the contours show you the water table, and then the depth to that water table is the colour. And of course, it's underground, it's subsurface, you can't see it, but here it is characterised. Now, in terms of dynamics, the groundwater goes up and down with the tides. At some sites, it goes up and down quite a bit. So perhaps a full tidal range at Kennedy Street's 500 millimetres. So one out near the coast has a 500 millimetre tidal shift. And it was this site that scared Dunedin, I think, early on, because they thought that maybe the whole area was subject to this degree of tidal fluctuation. But in fact, most of them are around 8 millimetres or so, or 17 millimetres in this one. Most of them are very small tidal shifts. And this is a plot showing you distance from the sea and the log of the tidal shift. And although we have a couple of places where there's strong tidal response, most of it is non-tidal, essentially has very little tidal effect. So we can map out that tidal response, and these red ones here and here in the reclaimed land by the harbour and Bayfield High School, and in a very open sandy dune type sediment right here at Kennedy Street. But the rest of it is mostly non-tidal, very, very small tidal response. And in fact, you get a lag and a change in time across the city where this site here, for example, has its high tide when the city's at low tide, when the ocean's at low tide, and when the ocean's at high tide, this is still it's 360 minutes behind. So we can map out tides. We can also look at the chemistry of the water, and this is the salinity. And using electrical conductivity, you can map out what the percentage of water is, of seawater incursing into the aquifer, if you call it an aquifer. The point is that most of it's fresh water because of that blob and the elevation of the water sitting above sea level. It's mostly fresh and fed from the hills. So we want to make a model of sea level rise, and one of the simple ways to do that is to take this median groundwater surface and make an assumption that in the future, even when sea level rises, that we will always have some form of recharge from the hills, and that we'll always have a blob of water sitting in the land of some sort of geometry similar to this, that is above the level of the sea, that it's fed by fresh water flowing out. So we can take this median surface and we can add some value of sea level rise to it and lift that surface up by that sea level rise. So here's this median groundwater level plus sea level rise. And then if we add in what is the kind of tidal effect, because if we make the expectations that probably the problems are going to be at high tide or at some sort of high water level, we can add in the tidal amplitude and the tidal efficiency in this part of an equation to create a future scenario, which I've got here, which is essentially what does it look like at 30 centimeters of sea level rise, to give you a mean high water springs model of taking this geometry that we have here and adding on the sea level rise, in this case using NZC rise curves with or without land motion, and then coming out in this case without land motion at 30 centimeters sea level rise. So to show you what that looks like, here's the water table elevation starting point. We add in some mean high water springs, and then we start to add 30 centimeters of sea level rise, 50 centimeters of sea level rise, 80 centimeters of sea level rise. Now, of course, this is mostly happening as a function that's just the groundwater position, but it's below surface. If you do it as depth to groundwater, here's the depth to water at mean high water springs currently as a median value, and you can add on 30 centimeters of sea level rise, 50 centimeters of sea level rise, 80 centimeters of sea level rise, and you start to see that it becomes emergent and out of the surface by the time you're getting to these sorts of numbers. So that's a geometric model of sea level rise, an empirical one, and I guess it's important to think about the caveats and what does it do and not do, and where is it good and what it's not good at. And the first thing is to realize that it's a static model, it's not a dynamic model. It doesn't account for velocity. It's strongly empirical, and it's using the current values, which may not necessarily be the state as it gets closer to the surface. It doesn't, for example, account for changes in the water budget. If we have big changes in our rainfall with climate change, then the mass balance may change, and it can't account for that in the way that a fully dynamic model might. So there are definite limitations to geometric models. And I guess the key things of the fine print and the assumptions is that we're assuming that the water table is going to equilibrate with the ocean as it does now, that the tides are going to continue to influence groundwater levels at the same extent that they do now, and that the tides aren't going to change in the future. We're assuming that the processes controlling the present hydraulic gradients, they're not going to change sufficiently to alter the shape of the water table. That maybe if you went from one type of sediment and you rose up and you passed from, say, for example, a silty layer into a sandy layer, you may find that you're not going to keep that shape to the water table. And we're assuming that away from the coast, the water table is going to continue to sit at about the same elevated position with a hydraulic gradient down towards the coast, which is a simplification. And that the future range of tides and storms is in the future is going to be similar to those at present. So let's have a look. We'll go back to the bathtub model, and I've coloured up the elevation of buildings in New Zealand Vertical Datum 2016 and counted essentially in these ranges, essentially. How many buildings are sitting in there, and therefore within those ranges what that might look like in terms of exposure to groundwater rise under a bathtub type model. And when you compare it to a geometric model, immediately hopefully that will jump out to you that, hey, there's red everywhere, what's going on? Well, the geometric model, because it's sloping and it's close and it's higher above the sea level, actually presents, it suggests there's a greater exposure if you just took it at face value. And you can look at the numbers here, they're quite different of things that might, within those same ranges, what might be exposed is very different than a bathtub model. Now, just to highlight this, there's some work that my colleagues are doing at the University of Otago, and Quinn Nugent is working this up just at the moment. But here we have, under different scenarios for RCP scenarios, the geometric model in green compared with the bathtub model. So essentially it's just a graph showing you those two differences in those previous two slides. And where essentially the houses, it's the count in the number of properties here. Where they overlap is shown in the mid blue, and when it's only in the bathtub in light blue, and green here. And the key thing here is there's a big difference between the circle of the geometric model and the bathtub, and that difference slowly goes away as you increase the water level and everything gets drowned. But in terms of the rateable values and things, that there's a substantial difference between these two models. And the message to take from this is that the differences between our models, between a bathtub and a geometric model, are as great, if not greater, than the differences between the RCP scenarios, the sea level rise scenarios. And so while everyone's concerned about, which CO2 representative concentration pathway we're going to go down and where we're going to go and what the uncertainty is with that. And people are often obsessed by that huge uncertainty in those different possibilities. Actually, we haven't got our act together as earth scientists to really understand the effect of the different models that we have and the differences across them. It's really important that we improve what we're doing. And I think it was a real shock to my colleagues who work in finance to see how bad we were at doing things. But we've also got a more tricky thing, or in some ways a more tricky thing, which is the compound problem. So I was talking then about a simplistic model of groundwater. And in Dunedin, we have this problem that actually most of the problem at the moment is around surface water. And we have this hypothesis for our Marsden project, which says that over time, as the groundwater comes up, that because it's got this non-linear relationship and locally in some places connected, the infiltration of the rain comes down and sits on top of this, that over time, the amount of room for rainfall events shown here as spikes will decrease, such that the effect across the zero level, which is the ground level, means that you start to get flooding events. So here's an example here of an individual precipitation event that's causing flooding. And that because we have this change in our precipitation regime, and because of climate change, we're expecting greater sized precipitation events and more frequent precipitation events, that you may start to stack up these events so that you get more and more frequent flooding events that get across the surface well before the inundation of ground by the groundwater. That's the hypothesis that we're working to, and from a financial point of view, my colleagues are interested in the fact that of what it might do to house values. That over time the house value increases with inflation, but if you have a flooding event, it dips and then recovers, and then it dips and recovers. But as these events become more frequent, the sawtooth dipping and recovers becomes trickier, and that you may get to a point where the comfort zone for banks and insurance companies, it starts to fall outside of that quite frequently to the point that the house value can get written off or go to zero. And the hypothesis is that that could happen well before groundwater actually comes out at the surface. And the beauty of this is that when you start looking at finance markets, you're talking about people and their emotions and we're looking at future values and thinking about that rather than just how many houses. It's more around a whole lot of kind of financial and people-related processes. If you want to read a little bit more about this sort of dip and recovery, Quinn's just got a paper in press in the last few weeks. I think it's just about out. It's nearly there. So look for it. Have a quick search under price recovery after the flood in the Australian Journal of Agricultural and Resource Economics. So that's the first part of that. We're sort of breaking that apart and then trying to look at this part of the system. But in terms of Dunedin, how do we deal with that? How do we model it? Well, we can use empirical observations of how much in a rain event does the groundwater come up. So this is a map showing you what I call the rainfall recharge index, which is the change in water level for the amount of rain. And in some cases, it goes up 10 times. The water level goes up 10 times the amount of rain. So for a 10 millimeters of rain, you're going 10 centimeters of rise, or for 10 centimeters of rain, you're going 100 centimeters of rise. In other places, it's much more subtle. But you start to see variations across the city, which partly reflect infiltration, partly reflect the build-up of houses and hard surfaces. In other places, it's related to the geology and whether or not it's a sandy sediment or whether it's a muddy sediment. In other places, it's related to the quality of the infrastructure and the drainage. But we can take that and we can then work out, using the median groundwater level and the depth to water and the rainfall recharge index that we measure, we can make a map of essentially how much storage can we presently hold in the ground in terms of millimeters versus rain. And this is that thing here, and you see the dominance of the red area here, where you can only really take a light rainfall before the groundwater would come to the surface. And in some places there's plenty of room, and other places there's less. And immediately you can start thinking about, what would we, can we do? Where are the key areas that we need to make sure our infrastructure is working? So we can calculate this available storage, and we can start to do statistical things with it. So for example, here's this workflow of going from different depth to water under different sea level rise scenarios. You can see how that potential to store rain decreases as the groundwater comes up, and you can see it decreasing down here. I've chosen 4 sites in this map, but you can do it all over the place, and you can look at essentially how much is that storage going to fall, keeping in mind that Dunedin annually would have probably a 100 millimeter rainfall event. That starts to get a bit worrying. but then we can add to that what is the future looking like in terms of rainfall. So Greg Bodeker at Bodeker Scientific is basically generating a stochastic statistical weather generator depending on different SSP and RCP scenarios for climate change. And we can take these expected rates of and annual exceedance probability of different sized rainfall and how they will change in time to map the probability of getting groundwater emergence and what's the changes in probability at different sites. And I guess the key message that we're starting to see in that is that at 50 centimetres sea level rise, you really haven't got much more storage for any rain event in the city in Dunedin anyway. We're running out very quickly. So if infiltration goes from rain immediately into the ground, and it doesn't always, then we've got a problem. There are, of course, when you start thinking about these models, there's caveats that we need to throw in there. We're assuming that the infiltration rate and the connection between rainfall and groundwater remains constant over time, as defined by the Rainfall Recharge Index, and it may not. It may change as, for example, you get less efficiency in the drainage system, or you may get greater leakage from the drains. So that may not stay the same. And it may well be that, a lot of these things, that rain intensity is often much better to use than rain total, especially when you're talking about infiltration. So that could be developed a bit. And it's really lacking information on ponding and things. So it's not really a flood type hazard map. It's almost, it may well be, not as good as, the same problems that we have with the bathtub model, that we're not actually really directly looking at the hazard, and that we're sort of saying, this is the flood to the ground surface, but it's not necessarily the flood to floor level of the properties. And we really lack information, for example, in Dunedin of what are the variations in floor level and the vulnerability of the properties. So that's just an example of how you can use geometric models. And I just want to pull this back then in the final thing, just that to have a think about where this all may sit, and put this in context. And there's a lovely diagram here that I've got, which came out of a local government New Zealand report in 2014. And I've looked at this diagram a number of times and looked for all of the things that I'm interested in, like, eruptions and large tsunamis and large urban floods and that sort of thing. But this is kind of, a whole range of different types of risks. And the one that really stood out to me a couple of years ago was that there's this huge big human pandemic circle sitting up there with a reasonably high likelihood and a reasonably major consequences that I had kind of missed, totally ignored. And COVID-19 was a very rapid reminder of how these things evolve. But I wanted to put groundwater into this a little bit better. And so I've had a personal go at trying to pick up where I think hazards to and from groundwater might sit and what the effect of it is. And I've got various groundwater flooding events and saline intrusion and sort of potentially hazards to our drinking water and water supplies, contaminated drinking water supplies. But the big one to me is that groundwater inundation with sea level rise sits right up there. It's in this kind of zone between sort of major and catastrophic. And as sea level rise comes and starts to have a impinge on the coastal area where we all live, this is a really big sort of part of this picture. And at this stage, it's been missed. So I think there's a really good case for developing these empirical models of sea level rise effect on groundwater using the geometry. We need to go beyond just thinking around this hazard is equal to elevation, bathtub models. They're useful for regional assessments, like a country scale assessment, as you might see here. But when you get down to individuals and individual properties, they are not correct, and they're nowhere near site specific enough for you to stand up in front of a South Dunedin hui and say to somebody on one side of the room, sorry, your house is actually under threat, and say to someone else, your house isn't under threat. They also aren't very good for assessing options and for thinking about, where would we do different work for infrastructure and things, because they don't get specific at perhaps suburb scale. And I think that when you start to monitor and observe groundwater, you can get to suburb scale, maybe half kilometre scale variations that are important. And so I would say that we can use observations to develop these geometric models where we get these subtle variations that we can pick up and understand. And they enable us to do some pretty good widespread assessment of both hazard and risk. And we can take them into the compounded risk space, for example, with how rainfall interacts with groundwater, or how rivers and estuaries interact with groundwater. And I would say that they're an approach that we can use to then get into screening areas of concern, where we might then calibrate our observations and build much more dynamic models that could look at what is the effect of this mitigation strategy, or can we do this with engineering or something. And I guess the key message I want you to take away is that our physical models are really lacking and need to be developed. We need to invest much more in them and improve what we're doing, and get a much better understanding of the uncertainty, but also to be able to convey those uncertainties to our end users and to the people that are really dependent on us. So I think that's pretty much my time and what I wanted to say, and I guess I will leave that there and see if any questions come up.
Fantastic. Thank you, Simon. Yeah, please raise your hands if you have questions. Looks like James Crampton already has a hand up. Go ahead, James, and feel free to turn your cameras on as you're asking questions as well.
Hi, Simon. That was an outstanding talk. Thank you. Hey, listen, so in your discussions with the South Dunedin community, do you get a sense of urgency? It seems to me, we just hear this morning that Air New Zealand wants to hugely increase its domestic air travel. As a society, we simply have no urgency, no understanding, no grappling with the real issues. But do people on the ground in South Dunedin, do you get a sense that they really feel panicked? They have a sense of urgency about this, something that is inevitable?
Sense of urgency, I think, in South Dunedin is very much still towards maintaining the infrastructure that they have. Part of the flooding in 2015 and a lot of the problems they have are around keeping the mud tanks and the drains clear and making sure the contractors are doing that job well, because that's the problem that they currently have faced. Having said that, they have managed to get that contract sort of system sorted out. They've got a really good relationship going with the council now. It was vexed for quite a long time, I can tell you, but they now are looking very much towards the future and the planning. What they want and what they appreciate is understanding a lot more about what they're facing at a local scale. So they know that the sand dunes are good, and that sand dunes, the issue is the sea coming over the sand dunes and things, and there's lots of people turning up to these meetings. What's really cool about the South Dunedin hui is that it has become a really major thing. So we have 2 or 3 of them a year. We have all the politicians there. We have all the councillors and the mayor and everyone are at that meeting, right through to kids there running around playing with Lego. It's the whole thing, and you've got 300 people there for dinner together talking about whatever issues are on the table. And that is, it's looking for solutions, not just worried about the problems.
Great. Martha?
Yeah, thanks, Simon, a really great talk. I'm just thinking about Wellington, of course, because I live here. And I see that it doesn't look very concerning there, but I know that the business district actually has the most, you know, there's not many houses maybe, but there's a lot of money in the CBD, right on reclaimed land. What do you think about that concerns there? You know, will that be a problem?
I guess my feeling from being in Wellington is I'm always a lot more scared of an earthquake occurring when I'm in Wellington than a sea level rise. So you do have to think about holistically about where does it sit in hazards. I haven't mapped it as a hot spot in this diagram, although you know, certainly sea incursion at Lower Hutt and things, and Petone is definitely a thing. In the city, reclaimed land is typically, it depends on how it was made, and some Dunedin stuff is incredibly permeable. It's got lots of rocks in it and no not fine-grained material. Other stuff's less permeable because it's been pumped in there. My feeling is that the land's probably sufficiently elevated that there'll be groundwater all through it, but I guess I'm a bit less concerned about the CBD and things around Wellington as I would be, for example, out in the Hutt Valley and things. And there's no real information on on monitoring that I know of the shallow groundwater. I mean, the boreholes that you've been working on and things, they pop down through the aquiclude and into the deep aquifers. You need to be understanding what's happening in that very shallow water table in 6 metre deep holes.
Thanks.
Okay, Richard?
Yeah, thanks, Simon. Really good talk. As James said, always like listening to your pearls of wisdom. I'm just going to answer Martha's question, if that's okay. Because the big issue in Wellington is that the 1 in 100 year inundation event from storm surge becomes an annual event with 30 centimeters of sea level rise. So groundwater is less of a challenge. It's that storm surge inundation, and when you have 50 centimeters of sea level rise, that 1 in 100 year event becomes bi-monthly, and if you have 70 centimeters of sea level rise, it's happening every tide. So yeah, the CBD is screwed pretty much. We've got to do something about that, big seawalls maybe. In the Hutt Valley, I know that groundwater issues, there's a paper by Judy Lawrence and a student, Rob Bell, where they looked at the change in water table height and the effectiveness of the drainage system, and it's like about 30 centimeters of increase in sea level, and that drainage system just starts to fail. So yeah, there are some really big problems that I would say are actually more imminent than a big earthquake. So we've got to get onto that. One last point or question or encouragement I'd make here is there was a paper recently published, and I was hoping Frederica and Rohir would put their hands up, but they've just recently published a paper looking at climate change impact, looking at rainfall change and the change in water table height in the Heretonga and Otago aquifer region. And so it would be really good, if you're not already aware of that, Simon, to loop in with Frederica and Rohir's paper, because I think there's a lot of synergy, and then we link that into Lee's dynamic modeling, and we can really start to tackle this problem as you've highlighted we need to. So yeah, thanks very much.
Yeah, thank you for pointing that out, Richard. And I guess again it highlights that these are really vexed problems as to where the water comes from, and you can very quickly forget about one and not the other. And you need to bring them all together into one space and look at the combined hazard. And at this stage, it's very difficult for us to numerically do that at a scale that's important. And I guess that's the key thing too, is the Frederica and Rohir's work, which I was certainly involved reviewing. You have some quite large uncertainties. You have a big scale kind of overview, but you've also got to get down to the site specifics and the sort of property scale work, and that's the hard thing, and that's where geometric models have the ability to be spatially as well as temporally precise, albeit with uncertainties driving them that you have to be aware of.
Great. I think Giuseppe is next question-wise, and I'll just point out to everybody that Frederica did put the link to the paper in the chat if you want to get in and see that.
Thank you, Simon. Nice talk. My question actually goes exactly in the last thing that you mentioned. Like, can you explain to somebody that doesn't know much about these things what will be the feasibility or the complication of using nested models? Like, if you had static model that actually as an ensemble of static models that target the variables or the monitoring variables that you want to use eventually in the dynamical models, and you have that at a scale that it's pretty close to the grid that you had with your piezometers, and that you can use actually even the piezometers to validate that type of model. And then you nest aspects of what that model gives you out in a dynamical model that goes exactly. And basically you can use the dynamic model in the areas where you know that there will be the strongest impact, like those areas, for instance, that you have shown for Dunedin, very close to the groundwater level blobs, that it's like where eventually the water flow and direction goes towards a deep basin and so on. Could you comment on that just in general?
I think it can totally. I mean, we will use the best data that you can to calibrate the models or to test the models. I guess in a place, the real uncertainties really come down to the parameters such as storativity and permeability, and how well can you define those, and the need to, how much does depth, variation with depth actually matter? It's tricky to kind of put those in because we don't really have good information on it. But in places like Christchurch, where you've got all the CPTs that have been done post-earthquake and a whole lot of data on the soil behaviour index and a vertical 3D kind of model, geotechnical model, it could be possible to do all sorts of really cool things. It comes down to how much are we going to invest in this? How much is the country going to put into the science? At this stage, I think, what are we doing? We're probably investing 400 hours a year in modelling time and people's time in GNS into this sort of problem. So compared with the scale of the problem, to me that's a big underinvestment. I'd love to see us doing what you're saying. Let's go, but what are we going to sacrifice, or how do we generate the science revenue in order to do that, and where do we get that from, and what are we sacrificing while we do that?
Thank you. Stuart?
Yes, Simon. Okay, I echo all those other comments. Terrific. And just kind of to follow on for Pepe a little bit, I just want to make one comment first. That Bernard Hickey, he doesn't say, he says New Zealand doesn't have an economy. It says we have a housing market. It drives all our thinking, and yeah, I think you'd appreciate that. So from the point of view of where does this go next, I'd quite be interested to get your thoughts. That given that housing stock is the economy, then and given those hotspots that you've identified, so what is the number one thing that we should be doing next?
Well, certainly the Strand Marsden project is interested in this for the exposure of banks and the big banks to their mortgage portfolios, and what is that exposure, and how much is that, and what's the threat to the New Zealand financial system as a result of all of this. So we're trying to sort of look at that big scale picture as well as the local kind of how many houses, what sort of properties, and get to the individual level, and how much of it's pinned on the uncertainty of the physical models going into the financial models. So I guess there's a certain amount that's happening under our Marsden project there, and the Climate and Energy Finance Group at the University of Otago are promoting a lot of work in this space. I'm not sure the future of this. I guess,
for example, would you start to advocate putting piezometric borehole monitoring in Napier, Tauranga, Whakatane,
So
and Victoria.
yeah, I'd go back to my point here with the monitor and observe groundwater. In Dunedin, the network we put in for South Dunedin cost about $100,000, between $50,000 and $100,000 in its first year operation installing it. It's really, really cheap. And if you were to go and build anything now, any sort of piece of infrastructure, the amount of money that you'd spend in subground information would be huge. If you look at the assets that are in South Dunedin and the quality of that land, we know so little about it, and yet we've got so much built on top of it. So retrospectively, going and installing $100,000 worth of equipment and monitoring for that 1 year, and then probably an annual cost of about $50,000 to keep up the data set, means that we now know what we're fighting and we know what the options are going to start to look like. So I would be very strongly advocating for any of the areas, particularly with the hotspot areas on this map, but that they really need to be having these networks. It's not expensive to do it, and we should have them all over the country.
We have at least one more question, but as I'm conscious we're over time, I'd just like to thank everyone for coming. Thanks, Simon, one more time, and encourage you to come to our next talk after Easter with Vanessa Tanner from Heritage New Zealand. So thank you everyone for joining. And Richard, if you want to go ahead with your question.
Yeah, again, it was more of a comment, and to back up what everyone's just said, Stuart and Simon, we're sitting here talking about, and we've got this geo network, we've got INSAR data, we're trying to scale up SkyTem. There's a whole bunch of different things that we think we need for Aotearoa New Zealand, and it strikes me we just need to have a bit of a session, Simon, on all of these different monitoring systems and really start to push to government why it's critical to do a sort of an environmental geonet. I've heard many of our staff talk about an environmental geonet, not necessarily GNS by itself, but with partners across New Zealand, so that we can really try to track these problems and we talk about adapting to climate change, monitoring, looking for trigger points, tipping points. The only way we can really do that is by having these monitoring networks. So I think the time is right. The time is now with the information you're presenting and the arguments we can make. Let's start pushing government to invest. So we should get a group together, another one, but you should lead it. Thanks, Simon.
Thank you, Richard. And thank you also for the reminder that I should have said thank you to the Otago Regional Council for being great colleagues in Dunedin and looking after the network with me, and particularly with dealing with all of the data storage and import of data. We go out together and collect all the data and bring it down, but they actually do a lot of the work in looking after that data and taking it from our laptops in the field and getting it into the system and back onto my computer.
They also contributed quite a bit to the drilling, which is really good as well.
True, Phil. Yep.
Great. Any last questions for Simon? Looks like that's it. So thank you once again, Simon, for presenting online, and really interesting to hear your thoughts. And thanks everyone for joining and for the discussion.
Thank you all for your time. Cheers.